in experiment.
And we don't know yet.
Why is light so fast?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, a neural circuit for infanticide in mice.
And getting to the source of fast solar wind. I'm Noah Baker.
And I'm Nick Petrichow. Mammals are a group of animals that are particularly dependent on adults when they are young. Even mammals that start life able to walk are still weak and vulnerable to predators and dependent on their mothers for food. As such, adults, usually the parents, will care for the young, grooming, feeding and keeping them safe. However, these caring behaviours aren't the default. In fact, many adult mammals actually kill young. For example, when a new male lion takes over a pride, he will often kill the cubs fathered by a previous male. This is possibly a way to ensure the survival of his own offspring, and it's not just lions. Many animals engage in infanticide, even the humble mouse. In the wild, nearly 100% of virgin female mice, ones that haven't become mothers, readily kill mice pups produced by other females.
It's actually pretty remarkable how frequent it actually happens.
This is Dayu Lin, a researcher of the neural circuits underpinning social behaviours. She's interested in how this behaviour changes, as mice do not kill pups after they become mothers.
This switch from killing to caring is a very drastic change. And how the brains has been changed in order to accommodate this drastic behavior output is unclear. So our goal is to understand this process.
And in a paper in Nature this week, Dayu and her team have published evidence for what they think is the specific neural circuit in the mouse brain responsible for this switch. To find it, they started by looking at an area of the brain known as the medial preoptic area of the hypothalamus, or the MPOA, a region of the mouse brain well known for its involvement in maternal care. The team hypothesised that this region, involved in caring, must be linked to the areas involved in killing. Because you can't really have both behaviours at the same time, the team thought that there must be some sort of interplay between brain regions responsible for each of them. So by starting with the caring area, it could lead them to the one responsible for the infanticidal behaviour.
So we sort of going through 3 layers of narrowing down. So the first layer is that we look for regions that's connected to the MPOA. And then the second criteria is that these regions should be activated after infanticide occur. And our third layer of criteria is basically we manipulate each of the brain regions that's connected to the MPOA, and we see whether we can induce the infanticidal behaviors, the pup killing behaviors.
The team were able to artificially activate regions of the brain linked to the MPOA using several techniques, including optogenetics, where neurons are made sensitive to light and can be activated by shining a light on them. And they found that by activating a group of cells in an area called the bed nucleus of stria terminalis, the team could consistently and drastically change mouse behaviour towards mouse pups.
And we see that we can drive the pup killing behaviors very reliably and robustly. And conversely, when we inactivated this area, even the females, they were naturally infanticidal, they were naturally hostile to the pups, then we can completely shut down that behavior.
The team were also able to show that if they activate the area associated with caring, it shuts down the area associated with killing, and vice versa, showing that indeed these regions seem to counteract each other. With this in mind, Dayu and the team were then able to figure out what causes the switch in behaviour when mice become mothers.
So for the region important for the maternal care, we found that the cells become much more excitable. Versus this area important For the infanticidal behavior, it showed the opposite change. So the cells become less excitable.
Now, this work has been done in mice, but the brain region that the team found that drives this killing behaviour is present across vertebrate species. So it's possible that it could be involved in similar behaviours in other species, including humans. However, Daniela Pollock, a neuroscientist that looks at the neurological underpinnings of social behaviours who wasn't involved in this paper, cautions against making inferences to humans.
I think it is still quite a long way to go until we have an application for that in the human population, but it's a first stepping stone, I would say.
Dale also agrees that there's a lot more work to be done. For example, finding the root causes of why these parts of the brain become more or less excitable when the mice become mothers. And there are other things that need to be addressed. For example, why killing behaviour isn't seen in all lab mice, despite them having the same brain structures as the mice in this study, which may imply that there is a genetic component. In fact, Dayu and the team tried to activate this behaviour in a strain of mice known as Black 6 mice, a popular lab strain which rarely engage in infanticide.
And we found that actually the cells there are extremely resistant to firing. So that means the cells just naturally, they are quiet. So they cannot be activated. And of course, if they cannot be activated, they cannot drive the behavior.
In terms of open questions, for Daniela, she'll be interested in seeing if certain diseases or social conditions that mice experience could activate this brain circuit.
Would stress provoke activation of this circuitry? Would any differences in the housing conditions, such as crowding, that you would, from an evolutionary perspective, think would be relevant, modulate or activate this behavioral circuit? I think would be very relevant to follow up on the implications of this finding.
There's a lot more work to be done on this topic, but from Dayu's perspective, the interaction between the positive caring behaviour and the negative killing behaviour is key. So maybe future work will need to consider both sides of behaviours.
When we suppress the hostile circuit, we actually improve the maternal behaviors at the same time. So I think that an important implication is just that, we have to not only look at the positive circuit, but also look at the negative circuit. So they're kind of the two sides of a coin.
That was Dayu Lin from New York University Langone Medical Center in the US. You also heard from Daniela Pollock from the Medical University of Vienna in Austria. To find out more about this paper, check out the links in the show notes.
Coming up, how new data from the Parker Solar Probe might help researchers solve the mystery of where fast solar wind originates. Right now, though, it's time for the research highlights with Dan Fox.
There's a cyclone raging at the North Pole of Uranus. Storm systems have been spotted raging at the poles of Saturn and Neptune, but none have been definitively spotted on Uranus. But now, as the planet is approaching its northern summer solstice, its northern hemisphere is becoming more illuminated by the sun, and so is easier to study. Researchers have taken this opportunity to use the Very Large Array Radio Telescope in New Mexico to observe Uranus, discovering a dark collar ringing the planet's north pole and a bright spot at the pole itself. The spot appears to be warmer and drier than its surroundings, with stronger winds flowing inside it, all hallmarks of a cyclone. Hints of the storm had previously been seen in observations made in 2015, and the cyclone might have strengthened since then. You don't need to wait for the summer solstice to read that research, it's in Geophysical Research Letters. Researchers have discovered that some ants construct landmarks to help them not get lost. The desert ant, Cataglyphis fortis, lives in Tunisia's arid salt flats, and sometimes travels over a kilometre from its underground nest in search of food. Now researchers have found that these ants build tall hills on top of their nests that help the insects to find their way home across the vast, featureless landscape. The researchers found that nest hills deep in the salt flats are on average more than twice the height of those near the seashore, where the insects have other distinctive landscape features to help guide them on their journeys. To test their theory, the authors removed the hills from 16 nests and at half of these installed 2 tall black cylinders per nest to serve as artificial landmarks. After 3 days, ants at 7 of the 8 nests without landmarks began to rebuild the hills, compared with ants at just 2 of the 8 nests with the cylinders. The researchers say this building and navigation strategy adds to the list of ways that these ants have adapted to survive in the harsh environment of the salt flats. Find your way to Current Biology to read that research.
Up next, reporter Benjamin Thompson has been searching for the source of some solar wind.
In cosmological terms, the Sun is a fairly standard star. Mid-sized, middle-aged, relatively unremarkable. And yet, the Sun is absolutely essential for life here on Earth. Not least because it creates what's known as solar wind. These streams of plasma are made up of electrons and ions, and they create a bubble that protects the solar system and the living things in it from damaging cosmic rays. Solar wind is flung out at high speeds from the outer part of the Sun's atmosphere, called the corona, and since its discovery in the mid-20th century, researchers have learnt a lot about it. But there are still questions to be answered, as Stuart Bale from the University of California, Berkeley in the US explains.
We know that it comes in sort of 2 speeds, at least as observed near Earth, what we call fast wind and slow wind. So the origin of these different flavors of wind, the local sources on the surface of the Sun, that's been one of the big questions for a long time. And another question is, what is the mechanism that energizes it to help it escape the Sun's gravitational field?
It's known that fast solar winds in particular emerge from regions typically found at the Sun's north and south poles, called coronal holes, where the corona is relatively cool. And this wind can reach speeds of around 750 kilometers per second. But it's been hard to find out a huge amount about its origins, largely because, well, it's difficult to study something from so far away.
So most of what we know about the solar wind comes from measurements that have been made near Earth. And so the analogy that I like to use is like a waterfall. If you wanted to understand the source, but you lived halfway down a cave and you stick your head out, all you're going to see is, turbulent flow. And it doesn't really tell you very much about what's at the top of the waterfall.
To pinpoint precisely where fast solar winds are coming from, Stuart and his colleagues needed to get as up close and personal to the Sun as possible. And that required using a very specialised bit of kit, NASA's Parker Solar Probe.
The spacecraft is about the size of an oil drum, and on top of it is a roughly 3-meter diameter heat shield that gets to be very hot, around 1300 C, 2500 Fahrenheit or so. But behind that, you have a spacecraft that needs to operate at a little bit above room temperature. So we have this heroic thermal engineering system that takes that 1300 C front surface and reduces it to about 40 C in less than a meter. It's an extraordinary piece of kit.
The Parker Solar Probe was launched in 2018, and it's been getting steadily closer to the Sun. In 2021, the probe was able to observe the Sun from about 9 million kilometres away, which is very close in astronomical terms. From there, it could take a range of measurements, from ion spectra to plasma density and magnetic field strength. And these gave the team new insights into what was going on the surface of the Sun.
So the surface of the Sun, the photosphere, the white light thing that you see in the sky, is convective. Think of a pot of boiling water, and you see little convection cells in the water. The surface of the Sun is like this as well. And this convection motion creates magnetic fields.
The roiling convection cells cycle plasma around the surface of the Sun, but according to their new data, this process is having a specific impact on magnetic fields.
So where that plasma flows down into the Sun, it drags magnetic field with it. So the magnetic field that's generated by the convection is also transported by the convection, and it becomes very intense. So you're gathering magnetic field from other places on the Sun and pulling it down into this kind of drain. And in that region where the magnetic field is very intense is where we see signatures of magnetic reconnection.
Magnetic reconnection is a process through which magnetic fields collide, annihilating each other and releasing a lot of energy. Magnetic energy is converted into heat and kinetic energy at the scale of atomic bombs, with explosive results.
It heats the corona, it heats the atmosphere just above the surface of the Sun, and it's that atmosphere that then bursts out against gravity. If you think of Earth, we have an atmosphere that's in equilibrium with gravity, right? So gravity is pulling the atmosphere down, and the pressure associated with the temperature and density of the atmosphere pushes back, and it's relatively static. The atmosphere of the sun is given enough pressure from the reconnection process to actually expand out and escape gravity and become an escaping wind.
An escaping fast solar wind. The team's data support an existing hypothesis that magnetic reconnection is central to the creation of fast solar winds, backed up further by computer simulations run by Stuart and his team. But plasma physicist Christopher Chen from Queen Mary University of London here in the UK, who wasn't involved in this research, doesn't think the debate about how fast solar wind is made is quite over.
They're really nice observations in a region far closer to the sun than we've been before. Put forward a nice argument that advances the reconnection-based scenario. It does look at one of the potential mechanisms. There are others as well. So I think it makes a compelling case for there being enough energy in the reconnection to power the solar wind. Although, I think it's not the final story. I think we do need to do some more work in comparing it to the other scenarios as well.
There are several competing theories as to how fast solar wind is created, and Christopher suggests that it could be that actually there's a mix of things going on, which could ultimately explain the complexities seen in solar winds.
So I think one of the next things to do is really compare this idea against some of the competing scenarios for generating the fast solar wind, but then work out which combinations of these are happening at different times in order to explain the different variability in the solar wind that we see. So, we see various different types of solar wind with different speeds coming from different regions of the sun with various different properties. So I think being able to explain all of that variability will be a key thing.
The Parker Solar Probe is due to orbit even closer to the sun in the next few years and collect more data as its mission continues, which could help further clarify the picture. What's more, corona are found in more places than just the sun. For example, around black holes or clusters of galaxies, and Stuart hopes that learning more about how they're energized could help explain how they function, potentially even helping narrow down where to look in the search for extraterrestrial life.
We now know that there are exoplanets around other stellar systems, and for an exoplanet to harbor life, it would have to have an atmosphere, or presumably have an atmosphere, and that atmosphere can be eroded by a solar wind. We know from the Mars analog, for example, that atmosphere can be eroded by the wind. So understanding more about which stars have solar winds, the nature of those solar winds, how they're accelerated, how intense they might be, also has impact on the habitability of exoplanets.
That was Stuart Bale from the University of California, Berkeley. You also heard from Christopher Chen from Queen Mary University of London. To read Stuart's paper, look out for a link in the show notes.
Finally on the show, it's time for the briefing chat, where we discuss a couple of articles that have been highlighted in the Nature Briefing. Noah, what have you got for us to discuss this time?
So I have a piece that's been written in BBC Future, and it's all about the origin of patriarchy, which I have to say there's just a lot more depth here and nuance than perhaps I expected, which maybe is unsurprising.
Well, when there's depth and nuance, I think it's helpful to have a definition. So what do we mean here when we're saying patriarchy?
So patriarchy is a male-dominated society, I suppose. It's a society in which men hold power, or there is a distinction between the roles of men and women in societal norms in which men have more power and influence. And that's what many societies in the world are today, but importantly, not all societies, and I think we'll get on to talk about that.
And so this is about the sort of origins of such male-dominated societies. So what does this article tell us about how these things have originated?
Yeah, so this was written by a science journalist called Angela Saini. She's actually written a book about this, and it's kind of an exploratory article, which I kind of see as a bit of a précis to her much longer and in more depth book, where she's trying to sort of get to the bottom of this question of where the patriarchy originated from. And she actually opens the article with kind of an anecdote from London Zoo in 1930 when the baboon exhibition was closed down. Now, it was closed down as a result of quite a lot of violence on behalf of the male baboons. But around the 1930s, there were scientists that looked at this, and it was called Monkey Hill, was the name of the baboon enclosure. And they imagined that what they were seeing was sort of the ancestral origin of patriarchy. They were seeing that actually monkeys, baboons, historically had always lived in these violent, male-dominated patriarchal societies. Whereas that's actually not the reality. In reality, the discovery of bonobos, for example, much more closely related to us than baboons that live in a matriarchal society, a female-dominated or female-led society, I suppose. That was a switch to that perspective. But additionally, there's more than 160 societies in the world right now that are also not patriarchal, they're matriarchal or matrilineal, in which women have a higher power in the society across the world. And so there's a kind of a question here about where patriarchy originated from, because it doesn't seem to be something that's biologically programmed or evolutionary programmed into people. It seems to be something that's come out of society as time goes on. And so what Angela Saini's done in her research and in her book and this article is try to get to the nub of where it came from.
So as you say, it doesn't seem that this patriarchal society is universal, so something must have occurred. So pray tell, what did occur that perhaps led to these sort of more patriarchal, more male-led societies?
So what she's done is she's looked back through history, looked back at archaeological sites for sort of evidence as to where that came from. And she points to what has been referred to by some archaeologists as the first city. It's called Çatalhöyük. Apologies if I've mangled that pronunciation, in what is modern-day Turkey. And this is a society where if you look at the archaeological data, this is 9,000 years ago, I suppose, you don't see a distinction in the roles of men and women. So in many archaeological sites, you see distinctions in what people eat, where they live, where they work. But in Çatalhöyük, this doesn't really seem to exist. So you see men and women doing similar roles, eating identical diets. In fact, even the height difference between men and women is minimal at that time. There seems to be much more equal in almost every possible way. Since that point, something has changed. In modern-day Turkey, there's a patriarchy there now. So one leading hypothesis for some time has been that the thing that changed it was agriculture. So when agriculture started to happen, men have a physical advantage in terms of strength, and so therefore they started to gain more land and more power and so on and so on. But that argument has been kind of, poo-pooed by many people. Firstly, there has been a lot of evidence of agriculture long before patriarchal societies existed, and they didn't seem to immediately happen. Secondly, even now, half of farm work is done by women. So it's not that women weren't doing farm work. And so that doesn't seem to be the driver if you sort of look at the record. And what's proposed here is that an alternative driver is that the patriarchy was driven by power, by powerful people, not by the needs within a family, the needs to raise a farm or raise cattle or whatever, but very much something that's been societally imposed by those in power at the top, by the elites. And she goes in to explore exactly what that might look like.
So how might this have looked then? What were these people doing to sort of gain power, and how did that sort of lead to a more patriarchal society?
Yeah, so if we look at society originally, you might think that the societies exist and everyone kind of takes care of their own. They take care of their family unit, maybe their extended family. But in a world where societies get larger and you get people in sort of prominent positions within that society, then you start to look at what happens if you start to build more resources than you just need. You're not subsistence anymore. You're trying to build resources so that your society becomes more powerful than the neighboring society. And in that world, the elites start to prioritize different things. You're not just trying to subsist. What you're trying to do is you're trying to get more than what you need. And if you want to maximize that kind of efficiency, I suppose, you start to delineate within your society. So you start to say things like, well, actually, we need strong men to fight in wars, and we need women to make more men so that we have more people to fight in our wars so that we're more powerful. And so these societal delineations start to become imposed on people within the society more broadly by those in power that want to gain more power. And so that's where you start to get, the delineation within gender roles with what's expected within society. Men start to be, criticized if they don't want to go fight, regardless of whether or not they want to be a soldier. Women are criticized if they aren't particularly maternal or don't want to have children, because those things serve the wider society. And so the argument that's being made here is that it's powerful people at the top that created this division in which men ultimately have more power, because women are unable to do things. Men have fighting power, decision-making power, and women are focused on having children in order to grow the population and give them more resources to, fight those around them.
So there's this sort of like top-down way of giving people gender roles. So where does that sort of leave us today? Many of us live in sort of these patriarchal societies. Does knowing this or having this idea inform anything about how our societies are now?
I guess it's a question of how you look at it. I mean, to some extent, understanding the origin of these societies can allow people to sort of more analytically take apart what society is doing now, why people are expected to do things in the way that they are, and challenge that. So challenge situations where women are expected to do certain things or men are expected to do certain things. I think the key takeaway is that as you look into more details here and you realize that these are very much societally imposed distinctions and they aren't the genetic predisposition that was implied by Monkey Hill at London Zoo, you start to realize that these are also things that are within our power to change. You know, they are within society's power to change. It's something that we have modified in the past, and therefore, in theory, we can modify again. And there are hints that things are getting better. But of course, if people in power and the elites are the ones that have created this change, then, you know, from my perspective, it stands to reason that those people are also people that can have the most power to change it in the other direction. And so I suppose this is a lesson for all involved, but a particular lesson for those in power, which in many cases is men, to be a force for change in the other direction.
Well, fascinating stuff. I find this sort of anthropological histories really fascinating about telling us where we are today. But for my story, we're moving in entirely the other direction. I've been looking at something in maths, and I've been looking at sort of infinite patterns that go on without ever repeating.
I love a good math story, but I can already tell this is going to melt my brain. So a pattern that goes on and on and on and never repeats. Are we talking a number pattern, or are we talking a geometric pattern here?
So we're talking a pattern of shapes. So patterns of tiles might be the best way to think about it. And so I've been reading about this in Nature, and mathematicians have for around 60 years been searching for a so-called aperiodic, i.e. not symmetrical shape that can repeat forever, like on an infinite plane, and now they think they've found it.
So I'm imagining in my head here like a tessellating pattern of, you know, tiles, like a mosaic. So you can imagine triangles tessellating together. But in this world, the shape that is tessellating, it's the same shape that fits together over and over again, but the exact pattern of how they fit together never repeats. So it's continually a little bit different shape to shape. Is that a correct imagination?
Yeah, so you're right. This is basically a shape that you can tile together over an infinitely long plane, and it will never make a repeating pattern. There will be symmetries, so there'll be things that look symmetrical, but it'll never repeat exactly. It'll always be slightly different as it goes along. And so a shape was actually announced back in March of this year as being this one thing that can repeat forever. However, some researchers said at the time that actually you need two, because it needed this one shape, which looks a bit like a hat. The researchers named it the fedora. And you need this one shape and also its reflection. But now the researchers have come back and said, oh, actually, we've fixed it, and now we've sort of tweaked it slightly, and now you never get a repeat. So they made a new shape, which is very similar to the old one, and they made some other kinds of shapes that are similar and related to it as well, which never have this sort of repeating quality.
In my mind, when I'm imagining this, I am thinking that what the researchers have done is they've sat down with pieces of paper and cut out shapes and put them all next to each other and seen, oh no, that one repeats. And then do it again, then no, that one repeats. But I'm guessing what's actually happened is some very complicated formulae here, right? Is this all something that these mathematicians have created by thinking about the complex properties of geometry to come up with a shape? Or is it something that's been done by kind of trial and error?
No, you're actually right. It's the first one. So the main guy on this was actually a hobbyist mathematician, and he has spent the past 10 years trying to figure this out and has literally been putting different shapes together in this way, like you say, like cutting out shapes and fitting them together and see how they form. But also he used like a computer program to see like how it would go sort of ad infinitum. And after a lot of sort of tinkering about, he hit upon this shape, this hat, and then with some professional mathematicians, they published a preprint showing this shape, and now they've come up with their sort of tweak on the original shape, which is like that one, but a little bit better. But there is some very complicated maths involved as well, I'm sure you'll be happy to hear, which is the proof part of it. So to show that this never repeats, there's a lot of complicated maths that I could not get my head around involved, but mathematicians who have looked at this said it looks legit.
I mean, it's a fascinating challenge, I suppose, and I love that it comes from a kind of a hobbyist mathematician that wanted to find this out with paper and scissors. It's proper sort of 1.0 science and discovery, which is lovely to hear. Is there any reason that this is particularly useful to know about, or is it just one of those sort of factors of nature that's fascinating to find a shape that never repeats when tessellated?
It's mostly just for fun, as far as I can tell. We don't know if there is any particular use for this. There are these kinds of crystal type things called quasi-crystals that have a similar structure to this, so perhaps, and I'm reaching here, it could tell us something about that. But at the moment, as far as we know, it's just for fun. The one use for it is these patterns are actually quite pretty. So in the 1970s, Roger Penrose, who won a Nobel Prize recently for his work on black holes, showed that you could do this with two shapes. And then these two shapes have been fit together to tile the Oxford Mathematics Department's floor, and it looks very beautiful. So there is some sort of fun you can have with sort of architecture and design and that sort of things, but there doesn't seem to be any particular use to this. But it's very interesting that it's taken 60 years for mathematicians to find this. In the 1960s, it was thought to be impossible, and then it was shown that it could be done with 20,000 different shapes, and then later 104, and then in the 70s 2, and then finding just one shape has been a real challenge for a long time, but now researchers think they've cracked it.
That's fascinating. I hope one day to be able to buy a house. Maybe, one day. And maybe I will aim to tile my floor in an unlimited pattern. Because the shape is actually, I mean, it's very specific, but it doesn't look all that impossible to create. I'm sure a tile manufacturer could make an endlessly repeating tile pattern tile tomorrow. So maybe we'll see non-periodic tile patterning. God, I can imagine the YouTube tutorial about how to put that together in the future.
No, exactly. I'm sure this will be an interest to many tilers in the near future. But I think that's all we've got time for on the briefing chat this week. Listeners, if you're interested in more on these stories, you can find some links in the show notes, and there'll be a link of where you can sign up to the Nature Briefing for more stories like them.
And that's it for this week. Just before we go, don't forget you can keep in touch with us on Twitter, we're @NaturePodcast, or you can send us an email, podcast@nature.com. I'm Noah Baker.
And I'm Nick Petrichow. Thanks for listening.